Welcome to the second tutorial of MatCalc. In this tutorial we'll be performing a stepped equilibrium calculation. In the last tutorial we did equilibrium for a fixed temperature that was 700 degrees Celsius. Now we will be doing that for a range of temperature and see what happens to the equilibrium of different phases when we actually change the temperature. In the later part we'll be also seeing the equilibrium change when we change the carbon composition. So let's get started. As we did in the first place, we create a new workspace file, okay, and then we go to databases and select the same database that we used earlier. Well, you can use any phases as you like. You can change them at any time, you can add them at any time. Well, I'm just doing this because it is more general to use these phases for this system. So it's just an example, so I'm going to go with this. Okay, then we set the start values, and now what we're going to do is we perform stepped calculation instead of this which we did earlier. So as you can see, the temperature is the step variable here. You can change it to element content or carbon content or any other options provided here. So as the temperature is being changed, the range of temperature is from 1600 to 400 in Celsius. So the difference in temperature, the step is 25 degrees Celsius here. So it's good to go now. Okay, so what happened here? Actually, whatever happens is seen in the console window, but we do not have a console window because I accidentally canceled the window. So okay, so let's bring that back from here. This is called a quick access bar. You can access any of them anytime you want. You can always hide this doing like this, or make it appear anytime you like. You can hide these windows here, variables, doing this. It's very easy to use this. So what happened in the stepped calculation we can observe from this console here. So beginning from the very first, we see that the calculation had begun from 1000 degrees Celsius, and at 1000 degrees Celsius it was found that the only active phase was FCC, which is austenite, the face-centered cubic structure. And performing a number of iterations here, 1, 2, 3, 4 till 19, the only active phase is FCC. So we can infer that from the calculation here. Now this TSOL here refers to the addition or removal of a phase that is active, that has been active as their temperature is changed from 1450 to 1453. So we can see that at 1453.06 Celsius, one more phase is active. So this is not stepped at 25 degrees Celsius. As per the step, it should have been 1450 plus 25, which is 1475. But since for this liquid phase, the active temperature, the temperature at which it becomes active is 1453 degrees Celsius, so it has mentioned here that the new phase was added at 1453 degrees Celsius here. So at 20th iteration we can see that at 1475 degrees Celsius there are two phases which are active, which is liquid and FCC. So and there's another one, another TSOL at 20 after 20th iteration. So there you can see the FCC which was active in the 20th iteration has turned to inactive now. Okay, so in another TSOL, the BCC has been activated. So what happens in 21st iteration is we have the liquid, which was active first. We have the FCC that has been inactive after the 20th iteration, and we have the BCC that is newly activated. So what are the net activation? That are liquid and BCC. There's another TSOL, so you can say that BCC has been deactivated now. So there's going to be only liquid now, up to 1600 degrees Celsius. Now it changes the step direction. So the maximum range which we used was from 1600 to 400 degrees Celsius, and the iteration was performed had begun from 1000 degrees Celsius, and it had reached the maximum value of 1600 degrees Celsius. So what it does now, it changes its direction from instead of increasing the temperature, it now decreases the temperature. So that's the step changing. So we have already performed from 1000 degrees Celsius. So the next iteration it's going to be performing is below 1000 degrees Celsius, so which is 975 degrees Celsius here. So from 975 to 800 we have FCC, which was active. As we can see from the first iteration here, FCC was already active there, active at 1000 degrees Celsius. So it's going to be the same for 975 too, since there is no TSOL here. The active phase remains the same. Okay, it's the same for up until 750 degrees Celsius. Now, okay, here's another TSOL for FCC. That means the FCC, which was active till 800 degrees Celsius, has been inactivated now. Also, here's another BCC. See, another TSOL for BCC. It means that at 800 degrees Celsius, at 787 degrees Celsius, this phase was activated again. So here's FCC and BCC after that, and then FCC was deactivated. Now we have only BCC, and graphite was again activated, so we have BCC plus graphite now. So there's BCC and there's graphite. Okay, so from 725 to 400 degrees Celsius, which was the least range, the least limit of the range, the calculation which we performed was from 400 to 1600. So this is the last temperature where the iteration is going to be performed. So we find that the BCC and graphite are active at 400 degrees Celsius. So this is what we can infer from the MatCalc console for a stepped equilibrium calculation. We have performed stepped equilibrium calculation for a range of temperature. We can do that for a range of carbon percentage. So we can go to calc, stepped calculation, and instead of going to temperature, which we used earlier, we're going to go to element content. So the element content can be varied from 0 to 1.5. This is actually the variance of carbon percentage by weight, because the element here selected is carbon here, and the temperature is in Celsius. The temperature is going to be fixed. We can set it as anything, say 500. Okay, and the composition is in weight percent. So this is the range 0 to 1.5 is in the weight percent, and the 25 is going to be too large. So let's say 0.05. Okay, so it's all set here. Before we perform another stepped equilibrium calculation, we have to make sure we save the earlier one, because sometimes we need to save it for future uses. So actually this calculation was performed is called a buffer, so we can save this as a buffer here. Okay, so I have named this as t equals 400 to 1600. You can name it as anything. So this is actually the buffer which we created earlier. Now let's work with another buffer. So we got to create another one. Let's create it. This time we are going to vary the carbon percentage from 0 to 1.5 at 500 degrees Celsius, which is a fixed temperature here. So let's begin with this. Go to calc again, step calculation, go to element content this time, and put the range of carbon percentage 0 to 1.5. Okay, the temperature is in Celsius, all set. Okay, let's the temperature, let the temperature be 500 now. All set. So go. So you can see immediately the MatCalc console is updated. Now what we can infer from this is, in the first iteration you can see that when the carbon percentage was 0.4, the only active phases were BCC and graphite. So you can see that for 500 degrees Celsius, the phases which are active most of the time are BCC and graphite. See here till the end. Well, you can see it's changing the step direction here because we have reached the maximum value of carbon percentage by weight, which was 1.5 as we set it. So it cannot go further increasing from 1.5, so it's going to decrease now. So it's changing the step direction from 0.4. It's going to decrease from 0.4 to 0.35 here. So since there is no change in phases, it's going to be the same as the first iteration here. So it's BCC continued unless there is XSOL, which says that a new phase is either activated or either inactive after this line here, XSOL. So you can see that XSOL, which is similar to TSOL, which we found in the calculation for, okay, this TSOL, which we found in the calculation while varying the temperature, is similar to XSOL for the range of carbon percentage by weight. So it basically says that a new phase, graphite, has been either added or removed from the activation level after this very step. So at this particular carbon percentage of weight, the graphite phase is disactivated, or it has been inactive after this. So unlike this, the active phase. Okay, so this one, what is this one? This is 0. This is a very small number, so it's the least limit of our range, 0 to 0 0.5, 0 to 1.5. So this is 0. Okay, so we can see that the calculation time was 0.39 seconds here. Okay, so at this particular temperature, we see that BCC and graphite were the most active phases. Let's check it for another temperature. So we have done this for 500 degrees Celsius. Now let's do this for another temperature. Go to, okay, let's first create another buffer. Let's create another buffer for carbon 1.5 with 800 degrees Celsius. Okay, so go to calc, stepped, element content. This is 0, as you know that. This is 1.5, similar. Okay, now, oops, were we working with 800 degrees Celsius earlier? No, I guess we were working with 500. Okay, temperature is 800. Okay, let's go with this. Okay, now we can see that the most active phase at this temperature is FCC, unlike BCC, which was at 500 degrees Celsius. So we can find that as temperature changes, the active phases also change, and as the percentage of weight by carbon changes, the active phase change, but more slowly. So you can see sol here, graphite has been added. So the next active phases after this step are FCC plus graphite. Now there's another, there's a change in step direction, so it has reached the maximum value here, so it's going to decrease now. The carbon content is going to be decreasing. So at 0.35% is the weight of carbon, there's FCC as it was in the first iteration. We can infer that. Okay, there's another XL. We can find that BCC has been added, so the next active phases are FCC and BCC as well. Okay, so there's another XL. FCC has been removed because it was already active here. The XL FCC means that it has been it is inactive onwards. So the only active phase at 0 weight percentage of carbon is BCC. So that's what we can infer from it. Now let's see what this buffer, saving the buffer, has done. This is 0, carbon content is varied from 0 to 1.5 with 800 degrees Celsius. Now let's go to this one and see our data. We can see that data is safe here. Basically our range was 400 to 1600, which is safe here. Let's see for another one. The data is safe for this as well. This is 500 degrees Celsius buffer. So in the end, we did for this. So even this is safe. So that's what saving the buffer does, or simply that's the use of the buffer. That's all for today. Thank you.